all right, more problems. It's going to be awesome. I don't know if it's going to be awesome or not. At this point, I just feel like there's just so many problems. And again, watch the ones you feel like you need to. Soccer player starts at rest, accelerates forward, reaching a velocity of something and something. What's the average acceleration? I feel like that was a problem we solved already, but I'll solve it anyway. Okay, starts at rest, accelerates forward. Velocity. Okay, so acceleration, average acceleration is change in velocity over change in time, right? Because instantaneous acceleration is dv dt, so the average is just the change over and change over. So my change in velocity is I start at 0 and I go to 8. I start at time 0, I go to time 2.5. I guess I could have done that a lot easier, but I'm not particularly caring. So my average acceleration is 3.2 meters per second squared. Average acceleration, great. So what average force does the ground exert on the runner so she achieves this acceleration? Okay, sure, this is a question I always ask myself those 3 times a year that I go to the gym. Okay, so here's running soccer player. Running soccer player is going this way. See, once you get this thing, you don't actually have to, I was going to say try, but that's not real. She's accelerating at 3.2 meters per second squared, that direction. In her free body diagram, she is weight, normal force, and friction. And this is where you're going to freak out. What average force does the ground exert on her? Oh, okay, that's a garbage question. All right, there's obviously the friction on her shoes. Okay, and I've been telling you up until now, friction, even though we haven't officially talked about it in this chapter yet, friction goes in the opposite direction of motion. But I'm about to draw friction going this way, and you're like, but she's going that way, doesn't friction have to go the opposite way? Okay, this is where you have to get annoyed and you can't just turn your brain off and do problems. So think about my foot. And I'm running. If my foot is about to slip, the impending motion of my slippy foot is that way, so the friction on my shoe is keeping me from slipping, right? If I'm running, I don't know how to describe this better. I run, I hit the ground, and then my foot is like, you know, hopefully, if I'm trying to go forward, my shoe is like, I grab the ground. My shoe grabs the ground with friction so that I can go forward. If my shoe fails to grab the ground, and I guess this depends on, you know, my balance at the time, but for the purposes, I like it better to think about it as a wheel. Let's pretend my feet are wheels. Okay, so the wheel is turning like this, right? And you're like, clearly the wheel goes that way for me to go forward. So if the wheel slips, the wheel is trying to slip backwards, which means friction is going that way. Okay, does that make sense? I think it makes more sense with a wheel than with a shoe. So the wheel is going backwards, trying to slip going backwards. Therefore, the friction is trying to keep the wheel from slipping, so it's going forwards. And it's actually that forward friction that makes you go forward. So it's opposing the tendency to want to slip backwards, which is bonzo, and you just got to get over it. If for no other reason that if I drew it the opposite direction, how about this? Even if you're like, I don't want to learn this, this is stupid. If I drew the sum of the forces in the x direction, if I drew force the opposite way, there's no way a negative force gives me mass times a positive acceleration. Like, I just can't. A negative can't equal a positive. Therefore, the net force on the ground has to be positive to equal the mass of the person times her acceleration in the x direction. So you can either think about it from a physics perspective, think about it from a mechanics perspective, or just think about it from a, well, that's just how the math has to work in order for us to move on with this problem kind of a way. So the friction is the force that we don't know, so the friction of the ground. So the friction of the ground equals her mass, which was, I already forgot, 70. And the acceleration was 33.2 meters per second. So I've got some 70. So 224 newtons. So she needs 224 newtons, yeah, of force of friction with the ground in order to keep that acceleration going forward. So, you know, if her shoes are slippery, then she can't maintain that level of friction, which we haven't really talked about yet, but that's where we're going with that. Okay, let's do another one. Okay, we have a helicopter with a velocity. It's accelerated for 2 seconds. What's the magnitude of the resultant force during this time interval? Okay, so again, it's wanting us to come up with an average acceleration. Okay, so my starting velocities, well, I'll just do it this way. So my acceleration, acceleration is delta V, which way does a delta go? Delta V over delta T. So I started off at 0.5 and I went to 6.12. I started off at 0 and I went to 2 seconds. And I'm just doing that backwards for no reason. So I have -6 over -7 over -2. So 6, 7 over 2. So 3 I hat plus 3.5 j hat. And if that didn't make sense, I just did it with vector notation, but in parentheses. So 0 minus 6 is -6, 5 minus 12 is -7, and each one got divided by 2. So did I get that right? Okay, that's my acceleration. Okay, so what is the magnitude of the resultant force acting on the helicopter? So I don't know, because, I mean, I can't draw. So there's some kind of rando force. That's all I'm told. So the sum of the forces in general. So notice I'm not even doing this in the x or y direction. Is F rando, it's the only one on there, equals mass times acceleration of everything. So F rando is mass, which is 1.5 times acceleration, and this is where I mess up, is what is 3 times 1.5? 4.5. And what is 1.5 times 3.5? 4.2. Okay, so the rando force is 4.5 and 5.25. And that's, I think, all there is. What's, oh, the magnitude and the direction, or the magnitude of the resultant. Remember, the magnitude is the square root of the sum of the squares. So I can do that. I can square root the sum of the squares like nobody's business. Like, you couldn't even believe it. Sometimes people are like, holy Jamalama, did you just check out how she square rooted the sum of those squares? So 6.91. It's going to be funny when this answer is wrong. Oh, this is not meters, but this is force. So it's in, come here, girl. We're just not going to hang out anymore? Okay. Newtons. Let's see if that's right. 6.91 newtons. Yay! Okay. Baggage tractor. How many more of these are there? Holy mackerel, there's like a jillion of them. And then we'll get to friction. Okay. So I'll put these next two on the next video.